Hello everyone, we are back with another worked example problem from chapter 12. It's number 26. Number 26 says, a 1 kilogram ball and a 2 kilogram ball are connected by a 1 meter long rigid massless rod. The rod is rotating clockwise about the center of mass of the system at 20 RPM, rotations per minute. What net torque will bring the balls to a halt in 5 seconds? So a quick word on the wording of this problem. I actually changed the wording of the problem. If you look in the back of the chapter, it says the rod is rotating clockwise about its center of mass at 20 RPM, which is a little bit different than saying rotating clockwise about the center of mass of the system at 20 RPM. And that's the key there. That's the ambiguous trick that they're kind of pulling on us here. So I want to kind of clarify here, and you should always feel comfortable reaching out in an exam setting or in a homework setting and asking, or any setting, honestly any setting, and asking me if it's about the center of mass of the rod, center of mass of the system. How does that change things? If we kind of just quick draw our system here, I might put it like that. Since this is massless, I really don't care about giving it some depth or width or anything here. There. All right. So we have a 1 meter long rigid rod. If we were talking about rotating through the center of mass of the rod, right? Now there are a few key things that make this a little silly to say, but if we were doing the center of mass of the rod, it would be in the middle here at 0.5 meters. The thing that makes it silly is the fact that the rod is massless, so it's not actually going to be through the center of mass of the rod. It has to be through the center of mass of the system here, right? So if I have my 2 kilogram sphere or ball here and 1 kilogram ball here, my center of mass of the system is going to be biased towards the 2 kilogram ball, right? This is going to be my center of mass of the system. I'll just say center of mass here. Now, where is that? That's something that we're going to have to calculate, right? We're going to have to figure that out. I think before I want to do that, I know that I'm going to have to use radians per second, so why don't we just put omega in terms of radians per second, and to do that I'm going to say 20 RPM or rotations per minute, right? And I'm going to say 2 pi radians per 1 rotation, and then finally I'm going to say 1 minute per 60 seconds, right? And that conversion, minutes, rotations, I'm left with radians per second, and I get 2.09 radians per second. So that's the omega we're going to use here in this problem. All right, just kind of looking at this, what net torque is going to bring the balls to a halt in 5 seconds? So I have, if I'm casting these terms in a linear sense, I'm saying what force is going to stop this moving object? What force will provide an acceleration that will make my velocity 0? If I'm thinking back into this rotating reference frame, right, I'm thinking, okay, what torque is going to give me an angular acceleration such that my angular velocity goes down to 0 in 5 seconds? And to figure out that angular acceleration, I'm going to need my moment of inertia. We're putting the cart ahead of the horse just a little bit here. We still need to find that center of mass, but that's kind of the game plan here. I want to find torque. How do I find torque? Well, I got to do some rotational kinematics, right? I need rotational kinematics to find alpha, and then from that I can combine with, find I, and I'll get my torque from that, right? Because torque is I alpha. Mass times acceleration, right? Is force. Torque is I times alpha. So to find alpha, I'm still going to need to find my center of mass, right? So this is kind of the pipeline of what we're doing here. Okie dokie, let's start off with this, finding the center of mass. If we're finding the center of mass, our center of mass equation, x center of mass is equal to m x1 plus m1 plus m2 x2 all over m1 plus m2. We only have two masses, so that's why we're only going up to 2 here. And I can set an origin somewhere. I think it makes sense to maybe set the origin either right here or right here, right, at one of the endpoints, because if the origin is at one of the endpoints, one of these terms goes away to 0, right? I think in my notes I'm going to set it at the 1 kilogram, so this one goes to 0. And if I start to plug it in, so I'm going to say that this is 0. Actually, you know what? I'm going to change it up. I think I flipped my diagram on my notes and what I've drawn here. So I want to make sure that we have a positive thing. So I'm going to say that we have 1 kilogram of mass, right, 1 meter away, all over 3 kilograms, right? And that should give me 1/3 meters. And that makes sense now, right? With where my 0 is, right? This is my origin. I am 1/3 of the way through, 1/3 meters. The rest is to get to 1 kilogram. That would be 2/3 meters. I think this makes sense. I think this makes exact sense with what we're expecting. So this is our center of mass. This is where we're rotating around in our system. So now I can kind of move on to finding I, right? I total here. I total is going to be the sum of the i's, and since these are essentially point masses, yeah, they're spheres, they're balls, but I haven't really given them any sort of size here. There's no radius, and they're not rotating, they're not rotating about themselves here, so the moment of inertia of a sphere around itself is the 2/5 mr squared. In this case, what we're saying is I just have a mass rotating around a fixed point outside of itself, and so it's going to have, mr squared. Mr squared for I. So I'm going to say that I have m1 times how far away this is, right? And I'm going to say, well, I guess I could just say r squared, r1 squared. Let's just do it generally to begin with. r2 squared. Now if I'm actually writing this out, I am 2/3 of a meter away for m1. So I have 1 kilogram times 2/3 of a meter squared plus 2 kilograms, 1/3 of a meter squared, right? And when I calculate all of that out in a calculator, I get 0.667 kilogram meters squared. Alright, so that is our total moment of inertia. We are done with this part of the problem. I want to solve this rotational kinematic equation now to find my acceleration. So this is my initial speed. I know the time it takes to slow things down, right? I really do have 3 kinematic equations even in rotational space. I have omega f equals omega I plus alpha delta t. I have delta theta equals omega I times delta t plus 1/2 alpha delta t squared. And then I have omega f squared equals omega I squared plus 2 alpha, delta, theta. And so I think it's pretty clear that I want to use this first equation. It's the simplest. I know that my final velocity needs to be 0. My initial is 2.09 radians per second. I'm looking for alpha here, and then my delta t is 5 seconds. So what's my alpha have to be, right? My alpha has to be negative 0.418 radians per second squared. Now, a key thing is that this is clockwise. So technically, our omega is already negative. I guess alpha should be positive in that case. It's not a key thing here because we're only looking for the magnitudes of these numbers, especially the magnitude of torque here. So since it's the magnitude and not an actual direction, we're in the clear. But this is our alpha. So the only thing left to do is to multiply I and alpha together. All right. So if I take I alpha, talk about that as my torque, right? I'm going to get 0.667 kilogram meters squared times negative. And again, because it's the magnitude, I don't even care about the negative. It's just going to be 0.418 radians per second squared. And I see that I'm going to get a Newton, right, and then have an extra meter left over, and that makes sense because my torque is in Newton meters. What do I get? I get 0.279 or 0.28, I think is perfectly fine to say. 0.28 Newton meters. That's number 26. It's a little bit more complicated of a problem, especially the way that we've worded it. I've tried to make it a little bit better with the wording. I'm not trying to trick you guys, but this is a little bit more of an involved problem because there's multiple steps required to get to the end point. So if you have questions about that, feel free to email me or swing into an office hour.